In this second set of videos, we are going to talk about geodesics, and then we'll be going over cut points, bridges, and also the line graph of the graph that we're seeing here. So what we have highlighted in red here is an example of a geodesic from vertex 1 to vertex 3. Remember that a geodesic is a path in a graph that happens to be a shortest path. What I'd like to point out is that geodesics are not necessarily unique. For example, going from vertex 1 to vertex 3, we could go by edge E and then by edge D, or we could take a look at the sequence of edges that goes from edge A to edge B, and both of those are paths of length 2, which is the best we can do in this graph. So geodesics are great for traveling very efficiently from one point to another, but just because you found one geodesic doesn't mean you found them all, which will be important to us later on. Our next concept is that of cut points, and I really like a visual of this. Like, graphs can really represent very many things, but I like to think about graphs for cut points as representing people or places, and the edges representing travel between those places or people. And so a cut point is going to be thought about as like, what would happen if I removed this person or this place from our network of things? If I remove that person or place, then I might as well remove all of the paths that are associated with it because we can no longer travel there. And if I do that, what happens to the graph? Does it remain connected where I can get from every remaining landmark or every remaining place to every other? Or does the removal of this specific landmark break up what's left into pieces where we can no longer travel altogether now that that vertex is gone? And so visuals for this are very useful. We're just going to go through each of the vertices one by one to see if they're cut points. So when we take away the vertex 1, as I've done here by making it hollow and gray, and then I also remove the edges that correspond to it, the graph that remains in black is what would be remaining. And you can see that it's still possible here for each of those vertices, 2, 3, 4, and 5. All travel between those vertices is still possible. There's still paths between all of those vertices, even with the vertex 1 removed. So vertex 1 is not a cut point. Similarly, for vertex 2, we're left with vertices 1, 3, 4, and 5. And there's a very nice, easy way to travel amongst all of those vertices. So vertex 2 is not a cut point. However, vertex 3 is an example of a cut point in this graph. When we remove vertex 3 and the edges that correspond to it, 1, 2, and 5 are over here in a little connected component of the graph, and vertex 4 is all isolated over here by itself. And so that is our first example of a cut point. In fact, it's going to be our only example of a cut point because vertices 4 and 5, when removed from the graph, everything remains connected. So vertex 3 is a cut point. The remaining vertices in the graph are not cut points. Bridges are very similar to cut points, but almost a little bit easier because here we're not removing any of the places, any of the vertices. We're simply removing one mechanism of travel between them. So here we're going to walk through each of the edges and imagine what would happen if we just removed that single edge. Would the graph remain connected? Because this is much easier, all I'm going to say in this video is if you walk through each of these edges, you'll find that C is an example of a bridge in this graph. When we remove the edge C, we get that same kind of isolation we did before, where we have a connected component consisting of 1, 2, 3, and 5, and then vertex 4 is all over here by its lonesome. All the other edges, if you remove them, everything remains connected, and so they are not bridges in the graph. Last but not least, for this video, it's a good place for us to stop so that you can pause and just kind of look back and forth between the two graphs that you have on the screen. The left is the same graph that we've been dealing with throughout the whole presentation, and what we have on the right is the line graph. What we've done is where we had edges before in the original graph, those edges become vertices of the line graph. And we have a rule for connecting those vertices, and the rule is we will connect two vertices in the line graph if in the original graph the corresponding edges meet at a vertex. So for example, over here, vertex A and vertex B meet at the vertex 2. So when I go find the vertices corresponding to A and B, I should have a line between them, and I've labeled it with a 2 to indicate that that's why they're connected, because of that shared vertex. However, lines F and C over here do not share any vertices. So when I look at the corresponding vertices in the line graph for F and C, there is no edge between them because there is no shared vertex between those two edges. So you can pause and take a look to make sure that everything is kosher here, but it should be the case that everywhere there is a line between two vertices in the line graph, those edges share a vertex, and I've labeled them properly in this picture.